Okay, everybody, welcome back. This is part two of lecture 16. We finished part one by my suggestion you should do this quiz. So let's do the quiz. So these joint CDF questions are pretty easily answered by simply looking at what first principles. So the joint CDF of x and y is equal to the probability x is less than or equal to minus infinity, y is less than or equal to 2, and this is less than or equal to the probability x is less than or equal to minus infinity because this is a bigger event that includes this combination event as a subset. And of course, this is equal to 0. And so the joint CDF at minus infinity and 2, it's less than or equal to 0. So in fact, it has to equal 0. The next step is to look at the joint CDF at infinity and infinity. This is the probably x is less than or equal to infinity and y is less than or equal to infinity. And this event always happens. So this probability is 1. Next, we look at the CDF at x equals infinity and y equals little y. And this is probably x is less than or equal to infinity. Y is less than or equal to little y. But x is always less than or equal to infinity, so that joint event is just the event that y is less than or equal to little y, and its probability is the CDF of y. And then finally, uh, we have what's the probability x is less than or equal to infinity, and y is less than or equal to minus infinity. So once again, this event, x less than or equal to infinity, it always happens. So this joint event is the same as the probability y is less than or equal to minus infinity. And this event has probability 0 because y has to be something bigger than minus infinity. Just to repeat, here is the slide that duplicates the solution we just found. I also suggested you try problem 5.1.1, and so here we are. Let's do the problem. So to start, we observe that in part A, that this is simply the joint CDF of x and y at little x equals 2 and little y equals 3. And this is 1 minus e to the minus 2 times 1 minus e to the minus 3. This is the correct answer, even if it's not particularly informative. Part B asks you to find the joint the CDF of x, and that's equal to the joint CDF of x and y, where little x is fixed, but little y is infinity. So in fact, this is equal to the limit as y goes to infinity, 1 minus e to the minus x, 1 minus e to the minus y. The key thing to remember is that as y goes to infinity, the limiting value of e to the minus y is 0. And so in fact, this expression is going to 1. So in fact, this is equal to 1 minus e to the minus x. So this is the correct expression for all x greater than or equal to 0. You also have to keep in mind that for x less than 0, you have to use the condition of 0 otherwise. And so for x less than 0, the joint CDF of x and y is equal to 0. That also implies that the CDF of x is equal to 0. So we have a 0 here. And finally, if we combine these facts, we obtain this is 0 for x less than 0, 1 minus e to the minus x for x greater than or equal to 0. And we see that from this joint CDF that x is actually just an exponential random variable with parameter lambda equals 1. And if you look, the situation with x and y is symmetric. You can repeat the same steps for the CDF of y. By symmetry, y has CDF, Fy of y, which is 0 for y less than 0, 1 minus e to the minus y for y greater than or equal to 0. The joint CDF is the fundamental model for describing a pair of random variables x and y. However, we've seen that, in fact, using the joint PDF is a big pain in the butt. So starting in this section, we're going to look at tools particularly for discrete random variables, and then later in section 5.3 for continuous random variables that describe a pair of random variables but are easier to use than the joint CDF. The first thing we'll look at for discrete random variables is the joint PMF. Joint PMF is exactly what you would expect it to be. It's a function of dummy variables x and y, such that it tells you the probability of the joint event that random variable x is equal to little x and random variable y is equal to little y. In fact, we've been doing experiments and modeling situations with pairs of discrete random variables as early as chapter 2. So let's go back to an old problem where we test two integrated circuits. And the result of each experiment, each test, is that the circuit is either acceptable or it's a reject. And, uh, and so now we're going to do this again where we test two circuits, but we're going to generate two discrete random variables. We're going to count the number of acceptable circuits x and count the number of successful tests y before you observe the first reject. So the problem says to draw a tree diagram, so let's get started. So the first test is either acceptable or it's a reject. And the second test is either acceptable or it's a reject. And as we knew from chapter 2, we have an outcome which is either, we have four possible outcomes: an acceptable, 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 reject, reject, then an acceptable, and reject followed by another reject. And we also know the branch probabilities are 0.9 and 0.1 for each sub-experiment. And this lets us label the probabilities of the four outcomes: 0.81, 0.09, 0.09, and 0.01. Our next step is to go back to first principles and recall that once you have the sample space of the experiment, all of the random variables you generate can be simply read off from the outcome of the experiment. So in this experiment, x is the number of acceptable circuits. And so in the first outcome, 2 acceptable, so x equals 2. And the second outcome, x is 1. And the third outcome, with 1 reject and 1 acceptable, x is 1. And here x is 0. And the next part of the experiment says, it's a little bit trickier. It says count the number of successful tests before you observe the first reject. And that's y. So when both are acceptable, then we have y is equal to 2 because we had 2 successful tests before we observed a reject. In the next outcome, where the first was acceptable and the second was a reject, we observed 1 acceptable before the first reject. When the third outcome, which was the first test is a reject and the second is acceptable, well, we observed 0 successful tests before the first reject because the first test was a reject. So y is equal to 0. And finally, When both are rejects, y is again equal to 0 because we observe 0 acceptable tests before the first reject. This is pretty tedious, but if you just simply focus on what the definitions are, you're able to write down what these quantities are. And so now we're ready to say, oh, what is this thing, the joint PMF? We have a bunch of probability facts. Like the first fact is that the probability x is 2 and y is 2 is equal to 0.81. Here we have the probability x equals 1 and y equals 1 is 0.09. Here we have probably x equals 1 and y equals 0 is 0.09. And finally, the probably x equals 0 and y equals 0 is 0.01. So what we have here are 4 probability facts, but we still have to write them as a joint PMF. On the previous slide, we found 4 probability facts about the pair x and y, and these are summarized here. And conveniently, these are the 4 possible cases for the pair x and y because these probabilities add up to 1 if you check. However, what we haven't done so far is write them as a joint PMF of x and y. Maybe the simplest way to express this joint PMF is just to simply assemble the function of the joint PMF of all x and y as a list of equivalent to these facts. So for instance, the joint PMF equals 0.01 for x equals 0 and y equals 0. It's equal to 0.09 for x equals 1, y equals 0. It's again 0.09 for x equals 1, y equals 1. And it's 0.81 for x equals 2 and y equals 2. And those probabilities add up to 1, and so we have to exclude all the other possibilities with a quick 0 otherwise to finish things. So the point here is that on the left we have 4 probability facts, and on the right we have a joint PMF of x and y that embeds those facts and the fact that all other x's and y's have 0 probability. So making lists of pairs of x's and y's to write down a joint PMF is pretty tedious stuff. So there are better ways of representing the joint PMF. One of those ways is using a table. So you write the joint PMF of x and y in the corner, and on one axis of the table, you label the possible values of x. And on the other axis, you label the possible values of y. And now you fill in the table with the x's and y pairs. So probably x is 0 and y is 0 is 0.01. Probably x is 1 and y is 0 is 0.09. The probability that x is 1 and y is 1 is 0.09. And the probability x is 2 and y is 2 is 0.81. And then you fill in all the other pair entries as 0 because in fact it's implied by the 0 otherwise. And now this table is an equivalent representation of the PMF. And implicit in the table is the idea that all values not in the table all have 0 probability. A third representation equivalent to the table and the list is to label probability masses on an xy plane. So in this case, x can be 0, 1, or 2. Y can be 0, 1, or 2. And we have We can make a bullet at, at the 0, 0 point and label it 0.01, corresponding to this entry. We can make a bullet at x equals 1, y equals 0, label it 0.09, corresponding to this entry in our joint PMF. We have 2 more points. We have 1, 1, and we label that with its probability mass 0.09. Then finally we have 2, 2, corresponding to our last entry, and it has probability 0.81. And And so this table of the joint PMF is one good representation, and another is this masses in the XY plane, where each mass is labeled with a weight that's equal to its probability. And of course, if on a test you're asked for a joint PMF, you could choose to make a list, you could choose to make a table, or you could choose the XY plane representation. As long as they're correct, you'll get full credit. And here's a slide that shows you the solution in the book. And the solution in the book is essentially the same, but it makes the specific point to keep in mind that there's always a function that maps the sample outcome to the pair. In this example, we called it G. And so G of acceptable was x equals 2, y equals 2. G of acceptable and reject was x equals 1, y equals 1, and so on. So it's good to remember that the pair of random variables is always the result of a point in the sample space. And of course, the solution in the book is the same, but just to recall, we can either represent this PMF by the table, or we can represent it by the masses in the XY plane, or we can represent it as a list. All three representations are fine, and you have to be comfortable with all of them. So now that we have some machinery for finding joint PMS, let's develop some tools for using the joint PMF to calculate probabilities of interest. The main idea here is to use this theorem 5.3, which is a kind of a bookkeeping theorem, in the sense that you're interested in some event B, and the way you describe this event B is in terms of the random variables x and y belonging to a set, and the set is B. The theorem simply says that if you want to find out the probability that x and y belong to the set B, then you just simply add up the probabilities of all the XY pairs that are in the set B. It's just a bookkeeping theorem. If that theorem seemed a little bit abstract, just keep this kind of picture in mind. Just imagine an experiment where there's X's and Y's, and the X's and Y's have non-zero probability on these grid points here on the plane. And then maybe the event B is that the sum of x plus y is less than or equal to 3. So the probability, so that event, here is the line x plus y is equal to 3. And then the event that x plus y is less than or equal to 3 is consists of all of these points in the gray area. Or another event is that, x and y are in a ball of radius 3 about the origin. So in this case, we think of B as this circle of radius 3. And then the probability that x and y are in this circle is the probability of event B And it's you find it by adding up all of the points that are in this shaded area. So going back to our simple example of testing two circuits, right? We had random variable x, the number of acceptable circuits, and y, the number of tests before observing the first failure. And in this problem, you're asked for the event b that x equals y. So, so b is the event x equals y, and we want to find the probability of b, which is the probability that x equals y, and that's equal to, by our theorem, the sum over all x and y belonging to the set B of the PMF of x and y. And now we need the actual PMF of x and y. By some cut and paste magic, I dug it up from another slide. Here it is in table form. And the rest of this problem is simple because all we have to do is look at the table and highlight the pairs where x equals y. So there's x equals 0, y equals 0, x equals 1, y equals 1, x equals 2, y equals 2. And all we're really doing here in this sum is saying, well, this is the probability xy is 0, 0, plus the probability xy is 1, 1, plus the probability xy is 2, 2. This is 0.01 plus 0.09 plus 0.81. And if I did this correctly, we have 0.91 is the final answer. Yay, I did it right. So we got the right answer. And now let's move on to a harder problem. So the joint PMF is really pretty simple. And to make sure you understand it, take this quiz. We'll start with the quiz solution in part 3 of this lecture.